Okay, good morning, class. Can you guys hear? Can you see the screen?
Yes, sir. Yes, sir.
Good morning. Is anyone there?
Yes, sir.
All right, good morning.
Yes, sir. Morning, sir.
No, my volume is down. Yeah, good. So you guys can see the screen. Right?
Yes, sir. We see the screen.
So today we're just going to continue on with simple harmonic motion. Right? Of course, doing some different stuff, but the same general concepts of simple harmonic motion. All right? So let's just jump into it and start doing questions right away. And when we come across new things, I'll just take a few seconds and maybe go over them a little bit so you guys can understand where they come from. All right, so let's just start with number 6. In the case of simple harmonic motion, define what is meant by periodic time, amplitude, and maximum velocity. Okay, now this should come pretty easy to you guys. Right? We know what simple harmonic motion is. It's some particle here. And this particle moves back and forth, right? Across some set boundaries. Now the amplitude is this distance from the center point, right? That D, right? That's the amplitude. How far away is it from this mean point or center point, right? That's the amplitude. The maximum velocity is the velocity when the particle or object is at the center point. So V here is V max, right? Or the maximum velocity when traveling through the system, right? So V max is the velocity at the center point. Now, periodic time is the time the object takes to make one complete oscillation. So what is that? Well, that's from the center going to one end, one extreme, back to the center, but not stopping here, going to the other extreme, and then coming back to the center, right? That's one complete oscillation. In the case of that sine wave, that's from 0 to 1 to 0 to -1, back to 0, right? This is one complete oscillation, right? One period. So the periodic time is the time for one complete oscillation, right? And that's pretty much it. Okay, so I trust you guys to be able to make these definitions by yourself, along with help from the handout and other sources that you might have. Okay. So now it's time for the real part, the actual calculations, right? A helical spring carries a mass of 20 kg at its lower end, and the spring stretches 25 millimeters when supporting 10 kilograms. When the mass is set oscillating vertically, the amplitude of the oscillation is 37.5 millimeters. Calculate A, the periodic time of oscillation, and B, the maximum velocity. Okay. Now, a few things that we have to figure out. So in order to find periodic time, we're going to have to find frequency, because T is equal to 1 upon F. Right? So we have to find frequency. And frequency is 2 pi. Let me just erase that. Putting it equal, but frequency is equal to 1 upon 2 pi omega, right? Omega times omega. Let me just write that like this. You just divide by 2 pi when you find omega. Now, omega Finding it in these particular cases is a bit different, slightly different from what we've been doing before. Now they gave us a mass and they did some experiment with the string using some other 10 kg mass. And they say when they use this 10 kg mass, the spring stretches 25 millimeters or 0.025 meters. So now with springs, how much it stretches or compresses depends on the force we apply to them, right? Let's say you have a spring, how much it stretches out or compresses in depends on the force we apply to it, right? And the force we apply to it, how much it moves, if it moves in a lot or a little bit, depends on the stiffness characteristic, right? The stiffness characteristic is what we denote as the letter E. So this E here that you would see when Mrs. So was teaching us characterizes the stiffness of the spring, right? Now the units for E is newtons per meters. The reason for this is because the more you try to compress the spring, the more resistance it gives, or the further you try to stretch the string out, the more resistance it gives. So the amount of force needed to compress the spring a certain distance, some delta x, right, varies. The amount of force needed varies with that distance that you're trying to move the spring, whether it's compressing it or stretching it out. So that's why it's Newton meters. Okay.
So what they're saying in the question is that the spring has a mass of 20 kg and then they added an extra 10 kg to it.
No, the spring, the helical spring carries a mass of 20 kg at its lower end. So there's some spring, right? And at its lower end, attached is 20 kgs, right? Good. Now, in addition to that, they're saying the spring stretches 0.025 meters or 25 millimeters when supporting 10 kgs. So separate to this, right? Separate to this, they did some experiment, right, with the spring, and they said when we apply 10 kgs onto the spring, it stretches 0.025 meters or 25 millimeters, right? This is separate. So this here, these factors here, these values here will help us find the stiffness of the spring. Right? Alternatively, they could have just told us, okay, this is a spring, it's holding 20 kg. E is equal to some value, right? E is equal to whatever value, 7.86 or something like that, right? They could have given that value. But instead, they told us when the spring is supporting 10 kg, it moves 25 millimeters. So that will help us find E. Okay?
Let me just verify. So we have one spring that has 20 mass and our next spring that has 10 kg mass.
No, it's the same spring. It's the same spring.
So
it's just spring. That at different point in time, before we set up this 20 kg, they tested the spring, right? And it stretches 25 millimeters when supporting 10 kgs, right?
Oh, okay.
So it's like before they put on this mass, they were testing the spring. They put on 10 kgs, right? And in the book, they had a ruler or whatever, and they were measuring, and they said, okay, 0.025 meters or 25 millimeters change, right? Delta X, change in length. That's how much it stretches. Good. Now, they did this so that they could get some value for stiffness of the spring, which will help in the calculations here. Now, the problem we're faced with is the spring and 20 kgs, right? These values here are just to help us find E, right? Because E, we need Newton meters. We need, that's 10 kg, which we'll of course convert to weight and divide that by the millimeters, which will give us Newton meters, right? Make sense?
Yeah.
Okay, good. Now, when the mass is set oscillating vertically, the amplitude of the oscillation is this. Calculate the periodic time of the oscillation and the maximum velocity. All right, so for periodic time, as I was saying, time, we know we usually find frequency and then invert it, find the reciprocal of that to find time. And for frequency, we usually get that from angular frequency, which is this omega sign here, W, and we divide that by 2 pi, right? So we need a formula for omega, right? So this is the formula here. But I want to show you quickly just how we get that formula, right? So F is equal to ma, right? Standard Newton's law. F for springs, right? The force for springs is that E times X, right? X is the distance, right? Because it's Newton meters. And then if we multiply that by the distance, this M and this M is going to cancel out, and we're just going to left with the force, right? Newton. So F is equal to ma. Change the F to E times X, right? Where X is that distance, right? S here is equal to M A, right? Carrying over, we get A. This A here is acceleration. Let me just put CC, right? To make sure that it's not confused with amplitude, right? So we get acceleration is equal to E times X divided by M, right? Now acceleration, we know in simple harmonic motion, right, is equal to minus omega squared times X, right? For simple harmonic motion. So now here, we can cancel out the X both sides, right? Carry over, divide, however you want to do it. And then carry over the square root. And what we're gonna be left with is omega is equal to E over M with the square root, right? Carry over to the square root this side. So omega is equal to square root of E divided by M. Okay?
Sir, I just look away for a minute there. How did you get omega squared there?
So acceleration, because remember, this is a simple harmonic motion system, right? We're doing SHM, right? So the old formula for acceleration, right, applies. So back into the previous handout that I gave you guys, right? Remember we had some formulas here, right? X is equal to A sine omega t, whatever. And then we had this other one, acceleration is equal to minus omega squared X. Well, same thing here, right? Acceleration is equal to minus omega squared X. Cool.
Sure, so how you drop the minus sign?
Ah, yes. Well, that's a good question. So technically, this force here is actually minus, right? This force here is actually minus because of the direction it's going, all right? This force here is actually minus. Yeah. Okay, so it would actually have a minus sign there. And the acceleration, how we characterize that acceleration, right here would be minus or plus depending on the direction. And this force would have to match that. So the math will kind of work out. Okay, so technically this EX is actually minus when you try and resolve it. Okay.
But
So
if you work and you leave out the sign, you won't get any complication.
no, you won't get any complications.
All right.
Yeah, so I mean, you can work without the sign. Okay, good. So we end up with this, right? It's not the most rigorous proof, but I mean, we got some kind of understanding that omega is equal to square root of E divided by M. Right? Let me just erase everything. That's pretty simple. I noticed that for the previous test, a lot of you guys forgot to deduce your expression for height. So a lot of you lost 5 marks there, right? So in this test, if you guys, for some reason, forget to prove that little expression, prove this expression, maybe you might lose some marks again. So if the question asks you to prove something or they do something, please do it because marks are awarded for that as well. All right, good. So now E.
Sir.
Yeah.
Sir.
Yeah.
So when you said deduce, is not just writing back the expression like actually.
No, you need to deduce, right? You need
like,
to
show how you derive the height expression.
Yeah. Yeah, you need to. All right, just give me a few seconds. Let me plug in my laptop. Okay, yeah. So when the question says deduce, that means like deduce, like come up with from your base example. Show your thinking, show your reasoning of why this is the equation. Right? So that's essentially building up a proof for that. Okay? It's not just writing back the formula. That's not deducing anything. That's just copying down the formula. Right?
But to show if everybody formula should get at least 1 mark for them.
No, I don't think so. You guys think so?
Yes, sir. We think this is fair.
No, but I mean, right, back the formula, that's like just writing back. Like anybody
could just show it, know the formula at least.
I mean, anybody could do that. Anybody could just write down a formula. That's not deducing anything. I don't think so. Yeah, it's just like, you know, just trying, like, you don't get marks for just the formula. Like, you get marks to knowing where that formula comes from and, you know, how you arrive at that formula. It's like if you submit a test paper and the answer is 2, and all you do is submit the test paper and write down the answer 2. Like, I can't give you any marks for that. Like, where the hell did this answer come from? You know, like you can't just write down 2. All right. Good. And I already give a lot of people -5 for that. So I'll have to go and remark like 50 papers. I don't want to do that. Okay. All right. Good. So E, we're finding E now. Okay. So E is, as I was saying, the newtons divided by the distance, right? The force divided by the distance. So since we're carrying this 20 kg mass, since we're carrying the 10 kg mass, in the experiment, right, we're using these 2 values, the 10 kg and 25 millimeters. These are the values given to us to find stiffness, which is E. So this 10 kg, the force applied to that as a result of gravity is times 9.81, right? Which will give you 98.1 newtons, right? Every kg gives us 9.81 newtons of force. 25 millimeters goes to 0.025 meters, right? Divide by 1,000. Plugging these 2 values in, here and here, just dividing them, we get E is equal to 98.1 divided by 0.025, which is equal to 3,924 Newton meters, right? 3,924 Newton meters. Now, using that formula we just found, omega is equal to the square root of E divided by M. This M here is the mass. It's just that I write a big M instead of small m. Right? That M is mass. Right, where M is mass, right? Now we know this to get the frequency, we divide by 2 pi. So we multiply by 1 upon 2 pi. And then we know to get the time, we divide frequency. We just find the reciprocal of frequency. So we take 1 over the frequency. So 1 over this is just going to be like flipping it, putting 2 pi on top. Makes sense? Because this here, let me just write that back, is essentially root E over M divided by 2 pi, right? This here is equal to F. So therefore, 1 upon F, flipping F, 1 upon F is equal to 2 pi divided by root E over M, right? So we end up with this general formula here. Okay. Now plugging the values into that general formula, T is equal to 2 pi divided by the square root of 3,924 divided by 20. Now we use 20 because we found stiffness already, and the question is actually asking for periodic time when it carries this 20 kg mass, right? So 3,924 divided by 20, find the square root of that, and 2 pi divided by the answer of this, whatever this evaluates to. So that there will evaluate to T is equal to 2 pi divided by the square root of 196.2. So T is equal to 0.448 seconds or 0.45 seconds, right? John, you can go ahead.
Yeah, sorry, just one thing again for the 20. How exactly get 20? Can you divide?
So, yeah, so 20 comes from helical spring carries a mass of 20 kgs, right? So in the system, when that mass is oscillating, right, when the mass is oscillating vertically, the amplitude is calculate the periodic time of the oscillation, right? You calculate the periodic time of the oscillation. So we want to calculate time for this 20 kg mass. This 10 kg mass is just the mass given to us to help find stiffness, okay?
Okay, sir, I don't understand.
The 20 kg is we're just plugging it in, right? We're just plugging in this 20 into our formula here. So remember we moved from here to frequency to time, right? You can calculate omega, that's perfectly fine. You can do that. You can go ahead and do that, calculate omega, then divide by 2 pi, calculate frequency, then 1 divided by the frequency and calculate time, right? You can do it step by step if you want, but I prefer just keep everything whole, keep all the variables in, then just plug in the values at the end and just get one final neat answer, right? Good.
Yes, sir, answer.
Good. So time is 0.45 seconds, right? Or 0.448 seconds. Okay, now for velocity, right? Maximum velocity. Velocity is a cosine function, right? So from here, come down back up. The maximum value of this cosine function is 1, right? It's 1. So we can just use that reasoning to plug the value 1 into this cosine formula. So the velocity formula is V is equal to A omega cosine omega t. We know cosine is going to go from anywhere from -1 to 1, right? We know the max value here. To get that max value out, we just put 1 in, right? You can use that reasoning, or you say velocity is max at the center, right? Velocity is max at the center, and at the center, x is equal to A sine omega t. So at the center, x is equal to 0. So when here, the sine omega t, so when sine omega t is equal to 0, cosine omega t is equal to 1, right? You can do this reasoning as well. Two people are raising their hands. Okay, so no questions. All right, so yeah, so V is equal to AW omega cosine omega t. This cosine omega t, we're going to replace that with 1, right? Because for maximum velocity, cosine omega t is 1. Two ways to reasoning that is saying that x is 0, so sine omega t is 0, so therefore cosine omega t is 1, or saying V is a cosine function, and the maximum value for cosine function is 1, so we can just go ahead and plug 1 in there. So we plug 1 in there, and we plug in our values for omega and for A. So back up to our question A, when the mass is set oscillating vertically, the amplitude of the oscillations is 37.5 millimeters. 37.5 millimeters goes to 0.0375 meters, right? Plug that in there, okay? Now we also need to find omega. Omega is the square root of E over M, right? Square root of E over M, square root of E over M. Here again, the square root of E over M, square root of E over M. So from our previous working, we just go back up and plug out this value for omega, which is square root of 196.2. Or if you had worked it a different way and you found omega, then you divide that by 2 pi and found frequency, then 1 divided by the frequency to find time. Somewhere along the way, if you'd found omega, you can just go ahead and plug that value in as well. All right?
Yeah. So, sir, could I see the other screen where you show when x is equal to 0 sine omega t is 1?
Here?
Yeah,
Yes.
thanks.
0 is equal to A sine omega t. So this A is going to cancel out, so it's going to be 0 is equal to sine omega t, right? Sine omega t is 0, cosine omega t must be 1. V max is at the center, right? So distance here is 0. Okay, good. So we plug those values in. We have V max is equal to 0.0375, the amplitude, times square root of 196.2 omega, times 1, right? Times 1. Plug this into the calculator, you should get V max is equal to 0.525 meters per second, right? 0.525 meters per second. Approximately 0.53 meters per second. Okay, any questions overall on this stuff?
So yeah, one for me, sir. For the V max, 0.0375. I understand the other two values. So the 0.0375, where exactly that came from?
That's from the amplitude, right? So in the question, I probably got too much stuff. Let me erase. Right? So looking at from here, right? When the mass is set oscillating vertically, the amplitude of the oscillations is 37.5 millimeters. So let me continue erasing. So 37.5 millimeters goes to 0.0375 meters, right? Just divide by 1,000.
Oh, I know, okay, sir.
Good, nice. Good. So now this A is the amplitude, right? Basic concepts of the formula. So you plug that value in. Plug that value in, using the others as well. Put into calculator, do it in your head if you can. V max is equal to 0.525 meters per second. Okay. Good. See there's a question in the chat. Matthew is not getting the same value for omega. Okay, so the value is for omega. Let's just do it from the top here. Okay, omega, draw a square, right? Pay attention to the square. Omega is equal to square root E divided by M, right? This M here is mass. So E, 3924. M is 20 square root, okay? Three, 924 divided by 20. 196.2, so square root of 196.2, right, which is equal to 14.007. So that's 14.01. So if you get this, that value there, then you go ahead and plug that in here. Remember, this is square root of 196.2. Okay, yeah. So remember, you can't use 10 kg. 10 kg is just a test value to give us 25 millimeters, which just tells us what the stiffness is. Okay. Okay. Yeah. So we end up V max being equal to 0.525 meters per second. All right. Okay. Any other questions? No, all right, good. So no other questions, moving on. I'll do this one as well. And then number 16, I'll let you guys give it a try so you can get some practice in, right? So number 13, when a mass is suspended vertically by a helical spring, the length of the spring is found to increase by 62.5 millimeters. If the mass is pulled 5 millimeters below its position of rest, then released, determine the time taken for one complete oscillation of the mass. Calculate also the acceleration and velocity of the mass when it's 31.25 millimeters from its position of rest. All right, there's a lot of things going on. So one, they didn't give us the mass of the spring. They just said when it holds this mass, it moves 62.5 millimeters, right? So we know omega is equal to E over M. So if we can somehow characterize E, because E is usually that M times gravity divided by some distance, right? Let's say, just say delta X. If we can somehow characterize E in terms of, in these terms, we can use this M at the bottom here to cancel out with the M inside there. So it'll end up something like this, right? So this here would be omega square root divided by M. So this M here would cancel out with this M, right? So that's the logic with these operations. So let's go about doing that. Doing it that way so that we can find omega. And then we can use omega to find time taken for one complete oscillation. So determine time, acceleration, velocity. Okay, good. So E is equal to M, that unknown mass, right? Times 9.81 divided by 0.0625. This 0.0625 comes from the value given to us, right? 62.5 millimeters divided by 1,000. Okay, good. Keeping it just like this because we want to cancel out this M eventually. All right, okay. So omega is equal to square root of M times 9.81 divided by 0.0625, and all of that divided by M again. Breaking down this fraction, right? We end up with something like the square root of M times 9.81 divided by 0.065 times M. So we have M in the numerator and M in the denominator. We cancel this out. And now we end up with nice smooth values here. Right? So we can find omega without ever knowing m, because E is a function of m, or E is based on m, as well as omega is also based on m. So those m's can cancel out. Okay, yeah, so someone's asking what E is. E is essentially the weight divided by that change in length, right? That delta x, right? That's E, stiffness of the spring. Okay, so now we cancel out these two m's. So we can just simply say omega is equal to 9.81 divided by 0.0625 to the power of 1/2, or the square root of 9.81 divided by 0.0625. Okay, good. Now T is 1 upon F, right? Which is 2 pi divided by omega. Do all the breakdowns, right? We find this value divided by 2 pi, right? And find the reciprocal of that. So we end up with T is equal to 2 pi over omega, right? As you break that down, which is just the same way we did it here, right? We did all our magic here. So now we're left with T is equal to 2 pi over the square root of 9.81 divided by 0.0625. So you plug this into the calculator, right? You get some value A, and then 2 pi divided by that value you get, should give you time is equal to 0.501 seconds, approximately 0.5 seconds, right? Half a second, right? This calculator. If you guys are working along with me, right, you should get the same answer. If not, just let me know. Okay, so time is half a second. Now, we found time. And the next things we need to find are velocity and acceleration, but at a particular point, right? Acceleration at a particular point when it's 31.25 millimeters. So let's just convert this right away. This is equal to 0.03125 meters, right? So when you see this number pop up, you know this is where it comes from, right? So the formula for x, which we know from previous simple harmonic motion problems, when finding velocity, sometimes you want to use the x formula with a particular distance so that we can use that to find the cosine omega part and then plug the cosine omega part back into our velocity formula, right? This is similar to your previous questions that you've been working before. So x is equal to a sine omega t, plugging the value for x, which is at 0.03125. The amplitude, right, is 0.05. The mass is pulled 50 millimeters below its position of rest, right? Below its position of rest. So amplitude is 0.05 times sine omega t. Dividing 0.03125 by 0.05, we get 0.625 is equal to sine omega t. Using your Pythagorean identity, which is 1 is equal to sine squared x sine x squared plus cosine x squared, right? We end up with cosine omega t is equal to square root of 1 minus 0.625 squared. Or whatever other method you want to do to find cosine omega t. Okay? For cosine omega t, yeah.
You could head back up a little bit for a minute. No, I mean, I can talk to the problem. I just want to see something.
Okay, let me clean it up.
Okay, all right, I got it. Thanks.
Okay, so since we found sine omega t, then we can use that to find cosine omega t, be it finding sine inverse of this omega and then omega t and then doing cosine of omega t and finding that value, or you use your Pythagorean identity, or you use a unit triangle where the hypotenuse is 1, right? However way you want to find it. So after we found sine omega t, we use that to find cosine omega t using that little identity we have there. So cosine omega t is equal to square root of 1 minus 0.625 squared. Breaking this down, we get cosine omega t is equal to the square root of 0.609375. Plugging this into a calculator, we get cosine omega t is equal to 0.781. At 0.781. So now we can use this to find v, because the formula for v is equal to a, which we know, times omega, which we know, times cosine omega t. This was the unknown. But we did some steps and we found the value for cosine omega t. So we can plug that value in.
Excuse sir.
Yeah.
Something I was wondering, right? This one, well, in this instance, right? Wouldn't x be different? Wouldn't x be the 0.03125?
Yeah, it is. But then we divided by 0.05.
Yeah. So what was coming to sir? I'm gonna annotate that. This part, sir, when we find the back omega now for the final part, wouldn't we use this new distance?
So this here is not the same as this here, right? What this is this. It's just a coincidence that those values end up like that. But this here is 62.5 millimeters, which is from our calculations for omega, right?
Mm-hmm.
It just happens that they kind of look the same, but this is actually 0.625 and this is 0.0625. They're not the same number, right?
No, sir, the X I was talking about, because what was coming to, right, sir? In this first instance, what I was thinking, right, this first instance here, this 3.125 that we, sorry,
there is no X in this formula. V, A, omega, cosine omega t. Yeah.
Excuse me, sir. When this video will be uploaded to YouTube?
Soon. After class. I'll try as soon as possible.
As soon as after class, sir? All
yeah,
right,
it usually takes a time for Zoom to kind of process the video.
Right now I'm getting a little busy, so I gotta come out of class.
Okay,
so this is what I want.
Well, you could watch it back later. All right, so the person I was...
All right, thanks, sir.
The person that was having the issue.
Yes, sir. This part was coming to the omega part, sir, where we had omega is equal to the root. And we just did what was it? The mass times gravity of these two would cancel out. So now omega is equal to G over X. Yes, sir. This part was coming to. Wouldn't this X change down here, sir?
That's not X. Well, that's not the same X.
Hmm.
Right? you remember E is kind of like a constant, right? E is kind of like a constant. So we found E with this value, this length, and this weight, right?
Yeah.
If we were to change the weight, then we'd have to change the length to make sure E stays the same. But after we find E, E is like a constant. E holds true because it's a property of the spring. It doesn't change. It's a property of the spring. So as long as we use two values where when we apply this weight, we get this length, right?
Okay, so to change the length, we'd have to also change the weight.
Yes. So E is a property. Remember, omega is equal to E over M, right? E, same. E is not changing, right? E is gonna, as long as we're using this particular spring, E is gonna be the same, right? Remember, omega is not, what is it? What did we break it down to? 9.81 over X. It's not 9.81 over X, right? Omega is E over M. It just so happens that we're allowed to cancel out and we end up with some
because the mass was the same, so it just cancel out.
Yeah. Okay.
All right, sir. Thanks for the clarification.
So plugging these values in, right? Plugging the value for A, plugging the value for omega, plugging the value for cosine omega t. B is equal to 0.05 times the square root of 9.81 divided by 0.0625 times 0.781, right? So you can simplify this, plug all of it into the calculator, however you want to do it, right? So V is equal to 0.05 times, simplifying this, 12.528 times 0.781. And all of that is equal to 0.489 or 0.49 meters per second, right? Meters per second. Any questions so far?
Sir, could you go back to the question? What did it ask us to find?
Velocity at that particular point. Velocity of the mass when it's 31.25 meters from its position. Okay.
Right, so we didn't need to find time and all of that.
No, because we kind of time is, well, we found periodic time, which was up here. We found periodic time, but time is kind of enclosed in the sine omega t function, which we kind of carried over to this cosine omega t function, right? So we kind of did find time without actually finding time. Yeah, because it's part of the sine omega t function. So we did it without having to find time. But technically cosine omega t, because this t is same as this t, obviously we could go through this function and then do sine inverse of this. Then we know omega, so then divide by omega and find t and then plug t into this formula, right? But all that's gonna do is give us the same 0.781. All that's gonna do, that's just, you could try it out if you want. It'll give you that same 0.781.
So the one that we're finding for, the distance, I think that's what the guy was asking just now. We plug it here into x is equal to a sine omega t.
This is, we're not plugging distance in here, you know, we're plugging omega. This is the value for omega.
No, I know that. I'm talking about the previous step where we have x is equal to...
Here. Yeah, we're plugging that distance in there. And we're using it to find the cosine omega t part of the formula. Right. Okay. All clear?
Yes, sir.
Okay. Now, time for acceleration. So acceleration is omega squared times x. What is x here? 0.03125 omega, right? Remember we found omega here as 12.528. Plug those values in, right? Acceleration is equal to 12.528 squared times 0.03125, right? Which is equal to 4.9 meters per second squared. And depending on the direction you're at, right? Remember distance, if distance is 31.25 millimeters, positive number, right? Acceleration is going to be negative because it's just simple harmonic motion. But magnitude of acceleration is equal to 4.9 meters per second squared. Okay? So that's simple for acceleration, right? Just plug the values in. Bada boom, bada bing, get your answer. Any questions on acceleration? Just using the formula.
Yeah, so one thing, just go back, sorry for this, but just go back one last thing.
So remember, we're finding, calculate also the acceleration and velocity, which we just did, of the mass when it's 31.25 meters from its position of rest. This system is a simple harmonic motion system. And with that, we know acceleration is characterized by this formula. Acceleration is equal to minus omega squared times x, where x is the position of the object, particle, or point from the center. Okay, so we can plug this 31.25 straight into the formula. But of course, we want it in standard units, right? 31.25 goes to 0.03125. We already found omega previously up here, 12.528, or you can go all the way up here and plug this whole value in. But we know this just evaluates to 12.528. Okay, we know that that's what that evaluates to because we did the calculation somewhere around here. So plugging those values in, right? Remember to square this and not just multiply the two, right? It's omega squared. Plug this into a calculator and you should just get 4.9 meters per second squared. Now there are other ways to work it, but this way is pretty simple. 1, 2, 3 lines, right? Yeah. Does that clarify?
Yes, sir, yes, sir, no, I understand.
I think Mr. Sill probably worked it a different way. And you can do it that way as well. It's perfectly fine. As always, more than one ways to work any question. You just find which way is easiest for you to remember so that you can do it in the test. And make sure the way you do it is clear so that someone marking the test can understand what it is you're doing. In case you make a mistake or something like that. Okay. So for number 16, I want you guys to do it. Okay, so a mass is suspended from the end of a spring and caused to vibrate. Show that its motion satisfies your definition of simple harmonic motion. Okay, so let me just do this part A, and then you guys will do part B. So part A. A mass is suspended from the end of a spring and caused to vibrate. We know that is just F is equal to MA, right? We're just kind of modeling the system, right? We break it down minus E to the X. It's minus sign because of how all the forces resolve out. Then we MA, right? Carry over, we get minus E over M times X is equal to A. Okay, A. Now, here we can just pretend that this is some constant K. So K times X is equal to A. Let me just get some water, guys. Okay, so as I was saying, we remember how we did this simple breakdown. F is equal to ma e to the e times x is equal to ma carry over the m. What we end up here is some equation that shows that x is proportional to a, which is the definition of simple harmonic motion, right? We have some point, and as it moves, right, its acceleration changes, right? When it moves further away, the acceleration gets bigger, right? The acceleration gets bigger, causing it to come back this way. This here is velocity, mind you guys. And at this point here, when x is 0, right? Remember x is here, this distance. When x is 0, the acceleration starts to decrease, right? The acceleration is 0. So it's no longer accelerating anymore. It's going to start decelerating here. So x is proportional to a. And because this displacement or this distance is proportional to a, we can characterize it as simple harmonic motion, simply because a, for simple harmonic motion, is the same thing, right? It's just some constant times x, right? So that's just a simple way of showing that, hey, even with a spring, when it's vibrating, it's also simple harmonic motion. And you can fill that up with some words and extend your proof a bit longer, right, to completeness. But simply, that's the reasoning to show why the spring is also simple harmonic motion. Now for the question, which I want you guys to do. A particle, mass 0.34 kgs, vibrates with simple harmonic motion of amplitude 50 millimeters. The maximum accelerating force acting on the particle is 18 newtons. Determine I, the frequency of vibration, 2, the maximum velocity, so maximum velocity of the particle, and 3, acceleration at 12.5 millimeters. A few things to keep in mind when doing this problem. Here, 12.5 millimeters, right? So you're gonna have to equate x to that and use it like a minus omega squared x, something like that, right? For maximum velocity, that's at the center point, right? That's at the center point, right? So cosine omega t is going to be 1 already. So you know that as well. The frequency of vibration is a bit different, but essentially it's F is equal to ma. They gave us mass. We don't know a, right? This a here is acceleration, right? Acceleration. F is 18 newtons. Okay? 18 newtons. So now we can say acceleration is equal to 18 newtons divided by 0.34 kg. Okay, we should give us meters per second squared. Now, having found the acceleration, we can equate it to omega squared by x to find frequency. Right? We can equate it to omega squared by x. Now, this force we put in, the force acting on the particle, is the maximum force. So for maximum force, distance needs to be maximum. So amplitude here is going to be 50 millimeters. So we can plug in the 50, and then we can simplify and find omega. And I think you guys, from omega, you can go ahead and find frequency and time and everything else that you might need, all right? And the other two parts of the question, maximum velocity and acceleration, is pretty straightforward. Okay, so take a few minutes and work this question I have the answers printed out there at the bottom, so you can verify as you go along. All right.
Excuse me, sir. Do you work this question in the YouTube video as well?
Yeah, why?
Oh, no, I was just curious if you just leave the question like this in the YouTube video.
Yeah. With all the dead silence and stuff as well. Yeah, I just kind of just leave the entire class. So like usually in the YouTube video, there's like just like a 10 or 15 minutes of just dead silence, right?
Oh, okay. Thanks, sir.
No problem. So work this question. If you guys have any queries, anything you want to know, maybe you get stuck, just let me know. I'll be right here. All right. So take maybe 15 or 20 minutes. The question could get a bit difficult, I guess. But just stay focused, and if you make a mistake, look through or you can just ask me for help and I'll try and help you out. All right.
Yeah.
Okay, how are you guys coming along?
Sir, I just missed the part. I went out for a little while. I missed the part that you were doing with the frequency.
Yeah. So what I was saying is, let me get a pen. Is F is equal to mass times acceleration, right? So we have 18 newtons and we have 0.34 kilograms. So we can use those to find acceleration. Having found acceleration, we can equate it to omega squared times x, right? This force that we use, maximum accelerating force acting on the particle is 18 newtons. So this maximum force comes at the end, right? At the end of this simple harmonic motion oscillation, right? At one of the ends here. So here, x is equal to a, which is the amplitude, right? So we can just go ahead and throw 50 millimeters in there. So we'll have omega squared is times 0.05 meters. Okay, and then we found acceleration. So we can use that to find omega. And from omega, I think you can find frequency, right? Right?
Yeah.
Good. Okay, so is anyone finished?
Yes, sir. I got back the same answers that you had.
Any questions?
No questions from me.
Well,
Excuse me, sir. The value for the acceleration, isn't it supposed to be a negative?
yeah, but we can just call it a magnitude and leave out the sign. But yeah, technically. And it just depends on how you measure things and how things are. Yeah.
Thanks.
Yeah. But magnitude-wise should be the same thing, right? So this 12.5 millimeters from the mean position. That could be either way, right? It could be this way or this way. It just depends on how you set up acceleration. Either way, it's going to be 13.24 meters per second in one direction or the other.
Okay, sir.
Is everyone else finished? Anyone stuck? Yeah. Okay, so if you're finished and you got the answers, you can go ahead and leave. Right? Mechanical students, we have class at 12, I think. Civil students, you can go ahead and leave. Enjoy the rest of your day, or if you have any other classes, you'll have to go to this, right? Okay. I'm not too sure whether or not you guys have a test this week, but I think there is a test next week on simple harmonic motion, right?
This is this week, sir.
The test is this week?
Yeah.
I don't think Mr. Sell notified me about that. Let me check.
Sir?
Yeah.
You could update me on the results for the last test.
I haven't marked. I've only marked about 50, so I have 90 more to go. I only got 90 more to go. Yannick Barrow?
Yes, sir.
Let me just double check.
I think you still, sir.
Just send me a message on WhatsApp and I'll reply there because I can't find your particular message. Right. So the same, right, whatever you used to send it as, just send me a message there and I'll verify. Okay. Any other questions?
Sir, could you do the last part for us with acceleration?
Yeah, do the acceleration for you guys. Sure.
Yes.
Okay. Acceleration at 12.5 millimeters from the mean position. So that's we gotta find omega as well.
I found omega already. Omega is 32.54.
Okay, so with omega equal to 32.54, then acceleration is equal to distance times that, right? Minus force square that times should be 12.0.125. Let me just use my phone. Yeah, I got the same answer. What did you get?
I was just trying to get it working. So I got 0.25 is equal to sine omega t. And then The acceleration formula.
Oh, okay,
is,
okay. So you use acceleration is equal to minus omega squared x, and then you broke down x into a sine omega t.
This is what I'm trying to use.
Okay. Yeah, so you should get sine omega t as something, right? Sine omega t
0.25 at sine omega t.
So this is minus omega squared. A is going to be 0.05 times this here, sine omega t, you got it as
0.25.
Good. So minus omega squared. So a quarter of this, quarter of that should be
13.56.
No, it should be this. Quarter of this. Half of this is 0.025 and half of that is 0.0125. Multiply these two numbers.
0.56 is the answer.
Okay. And 0.05 times 0.25. 0.0125, right? Good.
Times omega squared.
Good. So this here is the same as this here, right?
Yes.
So you should get the same answer.
Yeah, I got 13.56.
13.56. 32.54 squared times 0.0125. Let me do it. 4 squared.
No, actually got 13.24.
$13.24. Yeah. Good. So you got the same answer. Yes? Or no?
Yes, sir. Yes, sir. Yes, sir.
Okay, good. So what's the issue?
No, I think I was using 32.94, so I was getting.
Good. So 32.54. So whatever your omega value is, maybe you made a mistake plugging it in. Right?
Yeah.
Okay, so if you guys don't have any more questions, you can go ahead and leave. All right. I'll send out this handout by email and we'll upload the video. Okay. Enjoy the rest of your day.